going to talk about Taylor and Maclaurin series. And I mentioned the other day, we talked about power series and the fact that every function can be written as a power series. So today you're going to learn how to do that. You're going to learn how to write any function, any given function, to a power series. All right? And we gave the example the other day. We said, so for example, you have f of x, let's say, is the function sine of x. We talked about how you have your calculator doesn't have a bunch of values memorized for sine. It actually has the power series stored into it. So when you type a number into sine, it takes and plugs it into this equivalent polynomial, infinite polynomial, otherwise known as a power series. This was an interesting one. It alternated. You had all odd exponents and then the factorials. And this would go on forever. Okay, so this power series on the right-hand side is equivalent to sine of x. If I take and put a number into this polynomial, this infinite polynomial, this power series, it would be equivalent to sine of x. As long as I put a value in for which it would converge. And this is going to converge for all values of x. Alright, so our goal is to learn how to do that. How do we find a power series like that? That's the big question. How do you create a power series for a given function? And the answer is that there's a formula. The formula we use is called the Taylor series formula. Taylor series formula. So if I remember right, Taylor, it's a Brooke Taylor, I think the guy's name was. English mathematician, apparently came up with this little formula here. So this is used to find a power series centered at x equals a. So if we're going to find a power series, you got to be given a function and you got to be told what you want the center of your interval of convergence to be. So it's always focused around some middle of this interval, the center of the interval. All right. So the formula, it is a power series. So we're going to write it with series notation. We will start with n equals 0 and go to infinity. We will be using the derivative. So the first thing you're going to see here is you're going to be taking the nth derivative. That's what this stands for here, the nth derivative. So the first time, for the very first term, you put 0 in for n, and you would be the 0th derivative, which means no derivative at all. Then you'd let n equal 1, you'd find the first derivative. And n equals 2, the second derivative, and so on. And into that derivative, you're going to put the centered value, that a value, whatever the center is. Okay, so this is a derivative. Just consecutive derivatives.
So a is the derivative?
No. This is the derivative. A is the centered value. If this is centered at 2, a would be 2. These are consecutive derivatives here. That's just a small part of this formula. All right? Divided by n factorial times x minus a, whatever that centered value is. And we've already noticed that when we had a centered value, you can tell right away if it was centered because it was x minus the centered value. That was in the formula. To the n power. That's the general form. That's the formula right there. And it's kind of hard to see how this would work out in terms of terms. So we're just going to go term by term and show you what would happen. Let's start with n equals 0. So I want to find the 0th derivative. I want no derivative at all. I want the original function, in other words. So f of x, this, you know what I have here, is going to be equal to f of a divided by 0 factorial. And 0 factorial is defined as 1 times x minus a to the 0 power. And anything to the 0 power, almost anything to the 0 power, we know now, is going to be 1. So the very first 0, when n equals 0, the very first term is just f of a. Plus, now we're going to let n equal 1. So now we want to find the first derivative, f prime of a, divided by 1 factorial times x minus a to the first. Of course, 1 factorial is still 1, and x minus a to the first would just be x minus a. Now we're going to let n equal 2. So now we're going to take the second derivative, put in a, over 2 factorial times x minus x minus a to the second, and so on. Okay, so you're going to have just those consecutive derivatives, and then the reciprocal. Yeah.
So if the derivative we're taking, if the original function is not oscillating, will that mean it'll eventually, when you take enough derivatives, it'll be 0 over some factorial, which would just be 0 again? So it would eventually converge on 0?
Okay. That's an interesting question. Let's just, nobody's ever asked that before. Just a little side note here, because I think this will help you. Take a look at that function. If I wrote a power series for that function, guess what my power series would be? It's it. You found what I'm saying here? A power series is just a polynomial. This is already a polynomial. If you created the power series for this, you'd get this. And you'd get a bunch of zeros after, you know what I'm saying, like you said, the third derivative, 0 and beyond, then all those would be zeros. So there's no need to find a power series for a polynomial because what you'd be doing is writing a polynomial for the polynomial, which is itself. Does that make sense? I'm glad you asked that because I think when people say given a function, they think in their head something like that. But we're trying to talk about finding power series, in other words, polynomials for things that are not polynomials, like sine, cosine, tangent, e to the x, 1 over 1 minus x, things like that. That's what we're looking for, ln of x. That's when that's really helpful. You think about all the stuff in your calculator that you use your calculator to find, all those keys on there, those are all power series stored into your calculator. Alright? Does that make sense? So, that's just kind of a side note there. The theory behind this, just to kind of give you an idea of what's going on here, we've been doing tangent lines all along. So if you had an equation like this, let's say we're centered at A, the same equation we said, hey, find the equation of the tangent line. So the tangent line would be something like that. Use that to approximate it. Well, that's a pretty good approximation if you're close to this point. The farther you get away, then it's not that great of an approximation. If you stop here, right here, at the exponent of 1, this stuff right here, that's what you have. You have the equation of the tangent line. That's what that is. If you go to the next term, it's a quadratic equation. So now what you do is you get not a tangent line, but a quadratic equation that touches at that line, and it ends up being something like that. And it's a little better approximation. And then you end up getting this cubic equation that maybe would be something like this, and then the quad. And slowly you get, by having more and more exponents, you get a better and better and better approximation, to the point if you went on forever, it would be an exact match. Okay? So it's very, very, very cool. So, that's Taylor series. Now we have a thing called Maclaurin series. And I don't really know, I would love to know the history here of what happened. It seems like another case they're trying to give somebody credit for something that they don't really need to. Because the Maclaurin series is a Taylor series centered at 0. In other words, when you find a Taylor series, they always have to tell you the center. If they say to you, find this Taylor series centered at 0, you would plug 0 in for all those a's. And if they say to you, find the Maclaurin series, that's just code for Taylor series centered at 0. So, I'm not sure if Maclaurin came first. He came up with this formula that only worked at center of 0. And then Taylor came along and said, that's no big deal here. It'll work for everything. Kind of showed him up, but we feel bad for Maclaurin, so we still make sure you remember Maclaurin this way. Or if Maclaurin came second and said, oh, I'm so special, I'm going to steal the Taylor series, I'm going to name it my name if it's centered at 0. It'd be like me saying, every one centered at 5 is the Guy series now, and we're going to learn the formula for the Guy series, and that just means center at 5. Okay? I don't know what happened, but that's what it is. And the strange thing is, you need to know them both by name. So if they say on your AP test, find the Taylor series centered at 5, you know what to do. If they say find the Maclaurin series, they don't have to tell you the center. That just means the Taylor series centered at 0. Okay? And I know it can be confusing, but Taylor's the one that covers all of them. Maclaurin is the exact same thing, it's just telling you the center is 0. And you'll notice on the test, because they won't tell you the center, like, oh yeah, duh, this is the one that has to be 0, I would imagine. Okay, so specifically then, your function, whatever it is, if it was centered at 0, same story, we would start with the 0th derivative, in other words, no derivative at all, put the center at 0, so we put 0 in, plus, you would take the first derivative, put in 0, x minus 0, which would just be x to the first, over 1 factorial. I'll write that, even though it's just 1. Plus the second derivative, x to the second, over 2 factorial, and so on. Third derivative. Okay, it's the exact same formula. Yeah.
So it'd still be x squared?
Oh, shoot. Thank you. That's supposed to be a 3. Just seeing if you're paying attention. Very nice. Good job, you passed. All right. Any other questions? So you're going to be making them, and I imagine the first question is, when do we stop? Because these things go on forever, so they're going to have to tell you when to stop. There's a couple ways they'll tell you to stop. They'll either, tell you to stop when you get a certain exponent. So they may say like the 3rd degree, the 4th degree, the 5th degree. Remember, a degree is the highest exponent, so they might say that. Or they might tell you to stop when you have a certain number of terms. So they say the first 3 non-zero terms. Now, a non-zero term means a term that's not 0.